Hi there, thanks for stopping by. We're going to be wrapping up Chapter 8 in this video. You've been learning about special quadrilaterals, whether it's parallelograms, rectangles, rhombuses, squares, kites, or trapezoids. And what we're going to be doing in this section is summarizing all of that information more or less. The goal here is that you'll use properties of special quadrilaterals, the aforementioned special quadrilaterals, to determine the most specific classification of a given quadrilateral. Now, you'll kind of understand what that is once I get to examples later on. First, let's get to the business of summarizing what we've learned in terms of properties for special quadrilaterals. All right, now I have a few different charts that we're going to work with here. You can make it all into one chart if you like. Basically, we're going to have the same columns in all three charts, so all you have to do is keep going down your page here. I'll have, right here, these are all properties about the sides of special quadrilaterals, and then we'll go on to talking about properties of angles and then properties of diagonals. All right, so as far as you making this chart on your own, that's kind of how you can arrange it on your paper for your notes. Okay, so what I have here is simply a big chart where I'm wanting us to check off all of these special quadrilaterals that always have the indicated property. All right, so for instance, if I wanted to know which of these quadrilaterals always has all sides congruent to one another, well, we know that all sides of a rhombus are always congruent to one another, and we know that all sides of a square are always congruent to one another, so those two would have a check. Sometimes a rectangle would be equilateral, but if it's only sometimes, I'm not going to give it a check there. All right, you follow what I'm doing here? Now, preferably what's going to happen as we go through these tables is you'll pause the video and try to fill these in on your own, and then watch and hear my explanation as to why each answer is what it is. But, of course, if you're not confident enough to fill it in on your own, you can just watch me and fill it in along with me. And we're just going to go row by row here. All right, so the next property that I want to talk about is which of these quadrilaterals have both pairs of opposite sides congruent to one another. All right, well, that happens to be a property for parallelograms. Now, one of the things I want to get across to you here is that there are some shapes that if a property applies to that shape, it applies to other more specific versions of that shape. And what I mean here in particular is that rectangles, rhombuses, and squares are all versions of parallelograms, so automatically if I put an X in the parallelogram box, I'm also going to put an X for rectangle, rhombus, and square. All right, kind of similar to what I actually already did in the first row. A square is always a special type of rhombus, so if I put a X here in the rhombus column, it's got to go in the square column as well. All right, I think you'll follow along pretty well. For which types of special quadrilaterals are both pairs of opposite sides parallel? Well, that's the definition of a parallelogram, and thus it's a property for rectangles, rhombuses, and squares also. Where do you have exactly one pair of opposite sides that are parallel? Well, parallelogram has to have both pairs of opposite sides parallel, so that doesn't apply here, and it won't apply to anything else. It's a trapezoid that has exactly one pair of sides that are parallel to one another. So let's go ahead and put an X over there. And which figure has both pairs of consecutive sides congruent, but the opposite sides are not congruent? Well, that's the definition of a kite, is a quadrilateral that has two pairs of consecutive sides that are congruent. Whoops, I put that in the wrong box, didn't I? But its opposite sides are not congruent to one another. You get the idea of what's going on here? All right, great. So that's a summary of all the properties that we've learned in regards to angles. Now, sides. Now let's move on to angles. All right, so which quadrilaterals will you see all angles congruent to one another? In other words, which ones are equiangular? Well, that's a rectangle. And then since a square is a special type of rectangle, that's going to apply to a square as well. All right, in a rhombus and a parallelogram, it's possible for all the angles to be congruent, but they don't have to be. In a kite and trapezoid, it's not possible. All right, in which of these do you have both pairs of opposite angles congruent? Well, remember, showing that both pairs of opposite angles are congruent is a way to show that a quadrilateral is a parallelogram, right? So that's true in parallelograms, rectangles, rhombuses, and squares. All right, in which of these figures do you have exactly one pair of opposite sides congruent? All right, not both pairs, but exactly one pair. Well, it turns out that's in a kite. Remember, a kite has one line of symmetry, and so the opposite angles that are on either side of that line of symmetry are congruent, but the angles that are opposite on the line of symmetry are not congruent to one another. All right, you can look back at pictures of kites and kind of see that. In a trapezoid, the opposite angles are never congruent to one another. All right, and then how about with consecutive angles? Which of these special quadrilaterals have all their pairs of consecutive angles supplementary? That's going to be the parallelogram family again. All right, and in which quadrilaterals are exactly two pairs of consecutive angles supplementary? Well, that's in a trapezoid. All right, the angles between along the same leg between two bases are always supplementary to one another. But I mean that makes one pair of parallel sides, but the other pairs of consecutive angles cannot be, because otherwise it'd be a parallelogram. All right, and finally let's talk about the properties of diagonals and see which figures have which property. We've mentioned that some quadrilaterals have diagonals that bisect each other, and we've in fact said that it's a parallelogram. That's a way to prove that a quadrilateral is a parallelogram, is to prove its diagonals bisect each other. So then that works for rectangle, rhombus, and square as well. Now with a kite, you will have one diagonal that bisects the other, but they don't both bisect each other, so I'm not going to check that. In a trapezoid, the diagonals never bisect. Okay, well, I just mentioned this one actually. In which of the special quadrilaterals would exactly one diagonal bisect the other? Well, that's in a kite. All right, congruent diagonals. Well, you would have a rectangle if you have congruent diagonals, wouldn't you? Actually, that's only potentially, so you don't have to have a rectangle. We'll get to that momentarily. The diagonals are congruent, though. That is a property that rectangles have, and thus that's a property that squares have, right? Since squares are special types of rectangles. But you don't even have to have a parallelogram in order to have congruent diagonals, because remember, an isosceles trapezoid would have congruent diagonals as well. Now, is a trapezoid always isosceles? No. So I'm not going to put an X right here in the box. But a trapezoid does sometimes have congruent diagonals in the instance that it is isosceles. All right, perpendicular diagonals. Well, perpendicular diagonals is a quality that always pertains to a rhombus, and it always pertains to a square. And then it turns out it always pertains to a kite as well. All right, and in which of these figures does each diagonal bisect a pair of opposite angles? Well, that's something that we said is true for rhombuses and for squares. Now, this chart that I've gone through, this is something that you ought to be able to fill in. You ought to be able to identify all the quadrilaterals that have exactly one diagonal that bisects the other. All right, I don't think any of it doesn't make sense, because we're just summarizing information that you've already learned. But know that you need to know all of these properties. All right, now let's apply them in a few examples. I said the goal here was for you to be able to give the most specific name for a special quadrilateral given some properties. All right, well, that's the directions here for this problem, is give the most specific name for the quadrilateral and explain. And I have the information right here that the figures that I've drawn are not to scale. All right, so I don't want you to look at this and say, hey, it kind of looks like a trapezoid, because it kind of looks like this line and this line are parallel, and this line are not, and so this is a trapezoid. What I want you to do is think about what are the properties that I'm showing you this quadrilateral has, and then figure out what's the best classification that I can give to that quadrilateral based on that assumption. Okay, so I'm showing you two different things here. I'm showing you, first of all, that the diagonals are perpendicular to one another. Now I'm going to make a list of what that means this quadrilateral could be. We said a moment ago that a quadrilateral with perpendicular diagonals could be a rhombus, could be a square, could be a kite, and it turns out it could be other. It could be a non-special quadrilateral, just a random four-sided figure. And so let's see if we can eliminate any of these. Look at the other thing I've shown you about the diagonals. You notice how this diagonal and this diagonal bisect each other, but this diagonal and this these two halves of one diagonal are congruent, and these two halves of the other diagonal are not congruent. So I've got one diagonal right here that bisects the other one, but they don't both bisect each other. And since the diagonals don't both bisect each other, that's going to eliminate the rhombus and the square as options. And since we do have one diagonal that bisects the other, what that means is it is going to be a kite. It's not going to be another thing. So if ever you have perpendicular diagonals and one diagonal bisects the other one, guaranteed that you're going to have a kite. And your explanation can be that one diagonal bisects the other and the diagonals are perpendicular to one another. Okay, well, here's the next one. Let's think about what I'm showing you here. I've got one pair of opposite sides that are congruent to one another and one pair of opposite sides that are not congruent to one another. And then I have one pair of parallel sides. Now, if I don't tell you that a pair of sides is parallel, we're going to assume that they're not. So these, we're going to say, are not parallel sides. Well, the fact that it has one pair of parallel sides exactly already tells us this is a trapezoid. There's not exactly a big list of possibilities here. That's the only possibility. However, when I say it's the only possibility, this has to be a trapezoid, but it could be a more specific type of trapezoid. It could be an isosceles trapezoid, right? So we've got to eliminate one of these. Is it just a normal trapezoid, or is it isosceles? Well, if these are the parallel sides, that makes these sides the legs, and I've shown you that the legs are congruent to one another. So that means this is an isosceles trapezoid, and it's not just a regular trapezoid. And we'll say it's an isosceles trapezoid because exactly one pair of opposite sides are parallel, and the other pair of opposite sides are congruent. Now remember, if you had one pair of parallel sides that were also congruent to one another, that would make a parallelogram. But one pair of sides are parallel and the other pair of opposite sides are congruent. That makes an isosceles trapezoid. All right, one more example like this, and I've got to teach you how to read the information. I've given you a quadrilateral, and I've given you three angle measures with variables. What's the relationship between x and 180 minus x? Well, those are supplements, right? X plus 180 minus x just gives you 180. So what this picture is showing you is that this pair of consecutive angles are supplementary, and this pair of consecutive angles are supplementary. And when you're saying that one angle is supplementary with each of its consecutive angles, ultimately what you're saying then is that this can be a parallelogram. And if it can be a parallelogram, it could possibly be a rhombus, rectangle, or square. Well, which of those is the most specific name? We know for sure we can call this a parallelogram. Do we have enough information to say that it's a rhombus? Well, no, we don't know that all four sides are congruent. We don't know that the diagonals are perpendicular or bisect opposite angles or anything. So there's not enough information to say that it's a rhombus. We also don't have enough information to say it's a rectangle. Maybe it is, but there's nothing that says there are four right angles or congruent diagonals. And if we can't say it's a rhombus and we can't say it's a rectangle, there's no way we could say it's a square either. So the most specific name is a parallelogram. And the reason is that one angle is supplementary to each of its consecutive angles. Great. Follow along. I want to give you two more related problems with slightly different directions, and then we'll be done. Here I'm asking, is there enough information to classify the quadrilateral by the indicated name? So here, do we have enough information in the diagram, enough evidence to support the fact that this is a square rather than just a rhombus or a rectangle or a parallelogram, for instance? All right, well, let's think about what is being presented to us here. One of the things that's being presented to us is that all the sides are equal to one another. Well, that's a property that the square has, right? And then we're showing that we have one right angle. Doesn't sound like enough originally to show that this is a square. Because, for instance, does a figure with four congruent sides have to be a rhombus? How do we know the opposite sides are parallel? Well, if you remember the rhombus corollary, actually it says any quadrilateral with four congruent sides is a parallel. Is a parallel. Or sorry, I messed that up. Any quadrilateral with four congruent sides is a rhombus, which implies that it's a parallelogram, right? Because aren't both pairs of opposite sides congruent? So even though it doesn't show that they're parallel, we do know that the opposite sides are parallel. Now, knowing that this is a parallelogram, and more specifically a rhombus, The fact that we know this angle measure here helps us figure out every other angle measure, because remember, in a rhombus, the opposite angles have to be congruent to one another, so that would have to be 90 degrees. And the consecutive angles have to be supplementary. 90 plus 90 would give you 180, right? So we actually did have enough information to say that this is an equilateral parallelogram with 4 right angles, and so yes, we do. And the reason? Well, how about we say it's both a rhombus and a rectangle, all right? That justifies that a figure is a square. And square is the most specific classification because it tells the most properties that we can that pertain to this figure. All right, one more of these and we're done. Is there enough information to say that this is a rectangle? Well, what we know is that it's a quadrilateral, and I've shown you down here, or I told you that segment AC is congruent to segment BD. Did that because it'd be hard to mark on the diagram, but I'm saying that the diagonals, this diagonal, is congruent to the other diagonal. And so if a quadrilateral has congruent diagonals, that makes it a rectangle, doesn't it? Well, not exactly. Aren't there two different types of quadrilaterals that we learned that have congruent diagonals? A rectangle as well as an isosceles trapezoid. What we would still need to know to call this a rectangle for certain is we would still need to know, do the diagonals also bisect one another? Let me draw you a quick picture here. When you draw the diagonals of a rectangle, they don't only have to be congruent, but they have to bisect each other, which ultimately makes all 4 of those segments congruent to one another. But whenever you draw the diagonals in an isosceles trapezoid, what's going to happen is that they'll never bisect each other, although they will be congruent. And basically that means that these 2 segments end up being congruent, but these 2 segments down here are of different lengths. And we don't know which is the situation with this picture, right? We don't know if all 4 of these distances are equal or if just these 2 and just these 2 are equal. All right, so the answer is no, we don't know for sure that that's a rectangle. And the reason it's not a rectangle is because it could be an isosceles trapezoid in the event that its diagonals don't bisect each other. They look like they do, but we can't tell for certain. All right, so we're summarizing the properties of special quadrilaterals and expecting you within this video to be able to give the most specific classification you can to any quadrilateral given properties of that quadrilateral. Thanks for your attention, guys. Good luck with the chapter test that's coming up soon, since, hey, this is the end of the chapter, right? All right, see you later.